In class, you've been talking about compound growth and decay. So we're going to look at how this works. We know that the formula for compound growth and decay is A equals P times the quantity 1 plus R over N, raised to the power of NT. A is the final amount, P is the initial amount, R is the percent growth, N is the number of times per year the interest is compounded, and T is the number of years. So we're going to calculate a bank account where there's $1,000 initially, and it's compounding interest for 10 years at a rate of 8%. And we want to figure out how much money the account has if the interest compounds yearly, monthly, daily, hourly, and minutely. I'm not sure if that's a word. We'll use quotations around it. So what we're going to do is we're going to start with the yearly, which means my formula is going to be A equals my initial 1,000, 1 plus my rate 0.08, all over the number of times per year. Yearly is 1, number of times per year 1, and 10 years. And then I pull out my handy dandy calculator, and I put in 1,000 times 1 plus 0.08 divided by 1 up to the power of 10. And I get an amount that is approximately equal to 2,158.92. Let's see what happens when we go to monthly. A equals 1,000. I still have my 1 plus 0.08, but now I'm compounding monthly, so that's 12 times a year to the power of 12 times 10. The nice thing about my calculator is that I can actually not have to rewrite this whole thing. If I go to second entry, the entry I just had up there gets placed in here. And because I want to insert and turn that 1 into a 12, and then my power is now 10 times 12. So now I get I think I pressed the wrong button. Let's try that one more time because that answer definitely did not look right. That should be a multiplication. There we go. Okay, much, much better. I knew there was something wrong with that number. So now compounding monthly, we get an amount that's around $2,219.64. Let's go to daily. So daily, there are 365 days in the year. So my 12 turns into 365. I've got a small typo here. Let's fix that. 365 times 10. So again, put that into my calculator. I now need to turn my 12 into 3/6 and insert to get my 5. And I need to turn my 12 into 365. And my amount is $2,225.35. So you can see here the amounts are going up. The compounding more often means I'm making more money, but that the leap from yearly to monthly was a lot bigger than the leap from monthly to daily. Let's see what happens when we go to hourly. So A equals 1,000, 1 plus 0.08, and then I'm going to represent this as 365 times 24, because that's how many hours are in a day. So then I have 365 times 24 times 10. I'm starting to get more and more complicated here. So now when I insert, I need to actually say times 24. And up here, I need to add an additional times 24. And my amount is approximately, I have an error somewhere in this equation. Let's double check. I think we should have another set of parentheses here. That may make my life a little bit easier. Let's try that. There we go. So 2,225 and 53 cents. So in this case, going from daily to hourly only gained me a couple of cents. It didn't actually gain me any dollars. I'm not going to do the minutely because these numbers are getting pretty hairy here, having to input so many numbers. However, it turns out that the more times I compound, the closer and closer this formula gets to being A equals P e to the RT. So it turns out that this information, every time I compound more and more often, I actually get to a place where the numbers start becoming so much alike that we actually have a constant that we use for that, and the constant is E. So in this case, A is still our final amount. P is still our initial. E is a constant, meaning a number like pi. R is our rate, and T is the number of times the interest compounds. Now it turns out that we actually have two formulas, that this is actually our growth, and that we have one for decay also. The only difference being that my power is negative. So let's go back and look at the growth using the same amount of money we had last time. So we're back to $1,000. We're back to our rate of 8%, and now our time is 10 years. And let's see what happens when I put that into my calculator. Let's see how close it gets to the answer we have here. So I have 1,000. My E button is right here. It's the blue with the ln. E, and then I got 0.08 times 10. And you can see that we're getting really close. These numbers are really very, very similar. So the interest, when I compound it continuously, meaning more than every minute, more than every second, gets us to $2,225.54. So this is our growth, and this is our bank from the previous, when we were exploring what that interest equation did for us. Let's look at a decay problem. So a decay problem, let's say we have a rate of 4% decay. Time will do 40 minutes. And I'm going to use minutes here because I want to make it clear that when we're talking about growth and decay with these formulas, we're talking about how often it turns over. So maybe we have here some bacteria, 6,000 grams of something, or maybe radioactive substance, 6,000 grams of it. And the rate of decay is that every minute it decreases by 4%. So start with 6,000. My rate is negative 0.04 and 40 minutes. I have 6,000 negative 0.04 times 40. So after 40 minutes, I am left with approximately 1,000, 1,211.38 grams of this radioactive substance. Again, in this formula, the T is not the number of years, it's the number of cycles of decay or growth you're doing. So if your bacteria is growing every second, then your T is a units of seconds. If you're growing every year, then your T is a units of years.